Next, we're going to consider the transport of scalars by flow. So let's start by considering a scalar. So we're going to call our scalar here just C for the moment. Consider C. What is C? As a scalar, it might be something like smoke. It might be a dye. It might be something like temperature or pressure or density or other thermodynamic variables of the system. It's a thing that's a number, a value that changes in space and time, but not something that has direction to it. We don't know yet whether our scalar here, our C, is an active scalar, like temperature, pressure, or density might be, something that changes the flow, or a passive scalar, like smoke or dye are likely to be. Something that just is carried along with the flow. So it might be active, it might be passive. We haven't decided that yet. But any of these things might have a role. Okay, so how does C change? How does C change? What's the equation that governs the changes in time of C? Well, C follows a very sort of simple differential equation. It's the first that we'll meet in this form, what we would call a conservation form. The equation for how C changes with the flow, if there are no sources and sinks, is that d by dt of C plus the divergence of the quantity u C is equal to 0. This is the Eulerian derivative of C. And this is the divergence of the fluxes of C. The flux of C is equal to u vector, the velocity carrying C, uc. That's how C moves around as we carry it in the flow. All right, we have some other ways we can write this. That you'll see this in various forms in continuum mechanics. So we might write that d by dt of C, this is equal to minus the divergence of u vector C, then if we think in terms of these fluxes, flux vector, this is equal to minus the divergence of the fluxes of C. And if we know the fluxes here, it's just the velocities, then we know the evolution of C. In general, when we see an equation that takes the form of d by dt of some quantity, some q, whatever, is equal to minus the divergence of the fluxes of that quantity, we call this form a conservation form. And then we think of q as a conserved variable. Conservation form. And when we want to know whether or not a variable is conserved, we often go to look to see if we can put the equation that governs its evolution into conservative form. All right. I want to think a little bit about our equation here, and I want to try and rewrite it in some ways that can be illustrative to us. So let's take our d by dt of C plus the divergence of u operating on C is 0. So we can rewrite this term using vector identities. We can rewrite this, let's repeat our first term, d by dt of C plus this term expands out. The first bit is u operating on the gradient of C, and then we have the C times the gradient of u. This is just like the chain rule for vector calculus here. So here's our same equation rewritten with a vector identity where the divergence of u C turns into u dot grad C plus C div u. I'll remind you the u dot grad, these two contract on each other before they operate on the C, and in the same sort of way, the divergence here contracts with the u before the C left multiplies it. If you need brushing up on any of these sorts of vector identities, The Naval Research Lab's Plasma Formulary is a very convenient resource for this, and we have some links to this that you can follow. All right, so now that we've rewritten our conservation equation, we can see that the first part of our system here, this looks a lot like d by dt, the Lagrangian derivative, d by dt on c. And if we now write it, we've got d by dt of c plus c div dot u equals 0. Or, thinking of it another way, d of the c dt is equal to minus c div dot u. All right, so we can stop and we can consider a couple of cases of how motion might affect the concentration that we see in any particular parcel of fluid. So the Lagrangian derivative, this is the derivative of a parcel of fluid, and it's moving along and it's changing in shape and doing things like that. But the c inside of it, if there's no right-hand side, if it's d c dt equals 0, then you can change this parcel however you want. You can change its shape, but it's got the same amount of c spread throughout all of it. And that would happen if, say, the divergence of u was equal to 0. If the divergence of u is equal to 0, we call this an incompressible motion. And then the c doesn't change at all in any sort of way. All right. Well, we can think of two other cases right away. We could have a divergence of u that's greater than 0. This would be a diverging flow. What that would be is, that'd be something like you've got like a little parcel and the flow is diverging. That means that it's got a divergence. It goes outwards like this. And then your parcel becomes a bigger parcel, but it's got just the same amount of c now spread out over more space. It's diluted. It's diluted if there's a diverging flow. It's a dilution process. The alternative, right, is that we have div u is less than 0. This would be a converging flow. So now we've got like some like boundary of c, and the flow shown by the arrows here is like everywhere inwards. Now it's a converging flow, and you take something that's kind of dilute and diffuse and you smash it down into this tight little ball. That's a converging flow. And in a converging flow, we're going to amplify our scalar variable c by the actions of the flow. In all cases, c is conserved because it is following a conservative evolution equation up here. It's following a conservative evolution equation, but you can locally increase the amount of c if you have divergences or convergences of the velocity u. You can locally change its value in a packet of fluid if the flow is either expanding or contracting. And that's a very fundamental and important concept that we'll come across quite often. In general, when we have equations in this form where it's d by dt of a q plus div of u, we call these continuity equations. And sometimes you'll hear the continuity equation, and that's when c is the density rho. So if c is rho, and we have the equation d by dt of rho plus the divergence of u rho equals 0, which is also d by dt of rho plus u dot grad rho plus rho div u is 0. These are called the continuity equation, and this is the second equation that we need in our system of equations to solve our Euler momentum equation coupled with scalar variables. We have the Euler momentum equation, which is a vector equation, and we have the continuity equation, which is a scalar equation. We almost have enough now to solve our system.